Hello, and thank you for tuning in to the preliminary design review of the PetraDora team. My name is Oliver Davis, and I am the design team lead of PetraDora. Underneath me is our chief engineer, Andrea Dumitrescu, and then underneath her are 4 sub-teams comprising the main subsystems of the aircraft. The first one is propulsion, and that is being headed by Chris Parker. Next is the Structures and Mechanical Systems team, which is comprised of Angel Rodriguez and Jacob Johnson. We have Stephen Hicks leading the Aerodynamics and Performance team, and under him is Michael Blackwell. And then we have Andrea Gray, who is heading up software. The goal of this presentation is just to present a lot of the technical data behind our aircraft, which will give an idea of the preliminary design of the aircraft and how we expect it to perform once we construct it in the following semester. This project is a project that was originally started by the BYOBR team last year. They were tasked with creating a projectile that would have the ability to house an onboard flight data recorder. A different portion of this team has been tasked with creating the flight data recorder that would fit inside the projectile. The purpose of this presentation and this portion of the team was to design an aircraft that will locate the launch projectile to aid in the recovery of the projectile after testing, which will also assist in a better turnaround time for multiple back-to-back tests of the projectile and the flight data recorder. One thing to note for this presentation are blue boxes at the bottom of each slide, which will occasionally appear. The purpose of these blue boxes is just to state the purpose of the slide and just to make sure everybody is on the same page about why we are presenting what we're presenting on that specific slide. Some key terms to cover before jumping into the presentation are shown here. On the top left is DORA. That is our aircraft that we have been designing over the past semester. Underneath that is Petra. That is the projectile which will be housing the flight data recorder. And then on the right of the screen is Swiper, and that is the cannon that launches the projectile. This cannon was also constructed by the BYOBR team last semester. As shown here, with the arrow, that is the exit direction of the cannon. Just to clarify, because this image is a little lower quality, but due to the current situation, we are unable to get a better photograph of the cannon. Some similar aircraft are shown here on the screen. These aircraft are similar to ours in terms of the mission that they're used to complete. By this I mean they all have a similar range and endurance to that which we are seeking with our aircraft. They're also a similar size, so we used some of the aspects of these aircraft to come up with some initial designs of our own, shown on the next slide. The initial designs are shown here. These were quick mock-ups by our team just to kind of show some of the basic and main ideas that we had when designing aircraft in the very preliminary stages. As you can see, all 3 are quite different, and in the end, after a lot of contemplation, the bottom right aircraft is what we decided to go forward with. On the left of this slide, you can see the initial drawing or sketch of our aircraft. This was the very first design of it, and this is what we've been going off of from the beginning. And then on the right of the slide, you can see the current design for our aircraft. The requirements for the aircraft are shown below. The first requirement is that of a 45-minute endurance. This requirement was created to ensure that the aircraft could complete the mission to its fullest extent. The following requirement is DOR-02, that is our 2-mile range requirement. This is to ensure that the aircraft can fly up to a mile from the point where it is launched, complete its mission, and then return back to base while still having the ability to complete the whole mission. Another main requirement is DOR-07. That is that the aircraft have a maximum turning radius of 40 feet. This is to ensure visibility to the test engineers when testing the aircraft and the system as a whole. This will aid in the location of Petra, which was previously mentioned. I will now pass it off to Michael Blackwell to speak about the concept of operations of the aircraft.
For the concept of operations, Petra will be shot out of Swiper and travel a mile downrange. DORA will then be launched by hand and fly autonomously towards the impact site. A camera located below the fuselage will scan the ground for Petra. When Petra is located, the ground team will send a message to DORA to circle Petra. Once Petra is retrieved, another message will be sent to DORA to fly back to the takeoff site and land using a net. Once the data from Petra is uploaded, the entire process will be ready to be repeated within 5 minutes. The previous method of recovery had Petra sending a signal to DORA, but due to limitations within Petra, that is no longer a viable option. For the concept of operations for DORA, once Petra has impacted the ground, DORA will then be launched by hand. DORA will then scan the ground using a camera on the fuselage. Once Petra is located by the ground team viewing the video, a message will be sent to DORA to circle Petra. Once Petra is retrieved, a message will be sent to DORA to fly back and land using a hook in front of DORA and attaching onto a net. And now we're going to have Andrea talk about the constraint analysis.
We have our constraint analysis table. On the leftmost column, you can see all of the components that were estimated and evaluated. For CLmax, we estimated a value of 1.3. Load factor was determined by taking that turning radius of 40 feet from requirement DOR-7 and estimating at a bank angle of 55 degrees and a cruise velocity of 27 knots for airspeed, that we would have a load factor of 1.74. Our altitude density came from looking at the environment that we will be flying in. Furthermore, our power required and our planform area estimated values of 6 feet squared and 0.325 horsepower were derived from our wing loading and power loading, which came from our constraint analysis graph, which we can see on the next slide. In order to pick a wing loading and a power loading for DORA, we needed to create this constraint analysis graph to get a better understanding of what our design space would look like. Our red line illustrates our stall speed line, the green line illustrates the cruise speed line, and the gray line illustrates the maneuver line. Looking to the left of the stall speed line and above both the cruise and maneuver lines, we were able to pick the point of 1.05 pounds per square foot for the wing loading and 0.05 horsepower per pound for power loading. Now I'm going to hand it off to Jacob Johnson, who will be describing how our wing and empennage were sized.
Thank you, Andrea. So for our wing design, our main driving requirements were DOR 3 and DOR 7, being able to handle a 15 mile an hour crosswind or headwind or tailwind, as well as do a banking turn of 55 degrees in a 40-foot radius. For our main wing design, we went with a rectangular wing shape as well as a Selig 2091 airfoil. Our driving factor for this was we had to fit in a wing area of 6.26 square feet based on our design envelope to get the amount of lift needed for our weight. To do this, we went with an 82-inch wingspan and an 11-inch root cord, just so that we could hit an aspect ratio of around 7 to 8, and we nailed right at 7.45 to keep a pretty high Oswald's efficiency factor. For our horizontal stabilizer, we went with a trapezoidal style wing, and to find the area needed for this, on the right you'll notice an equation from Raymer, which is calculating for the total area of the horizontal tail, this being a function of the main wing area as well as the distance between aerodynamic centers, and then finally multiplied by a area ratio of 1/2. That 1/2 was found from trade study on similar aircraft, and that being said, we found that we needed an area of 0.95 square feet, and overall we got a 1 square foot. So being a little bigger, we figured would be better than having not enough. For the empennage and the vertical section, the design process was pretty much the same. However, for the area coefficients, we did have to increase those quite a bit just because the vertical stabilizer is in the wake of the fuselage for a majority of flight conditions. That being said, we went with a total height of 10 inches and kept the same NACA profile, as we did not want any lift in a opposite direction when we have a steady flight. And then this resulted in an area of 0.6 square feet based off of our ratio for areas to be 0.04. So shown here is the overall wing layout and how everything is going to be pieced together. You can see in the dashed lines the phantom outline of the aircraft, and you can see that we decided on a T-tail configuration for the horizontal tail, as well as the sizing reference and all that. Next, I'll be handing it off to Steven, who's going to be talking about aerodynamics as well as our airfoil profiles.
When selecting the airfoil for DORA, the driving requirements are DOR 01 and DOR 02. These are the range and endurance requirements. As a reminder, these requirements are 2 miles for the range and 45 minutes for the endurance. Looking at these equations, which estimate maximum range and maximum endurance for battery-powered aircraft, you can see that the primary impact of the airfoil, at least directly, is going to be in the parasitic drag coefficient. This is also the case for the general range and endurance equations, as well as these maximized equations displayed here. When we were determining our airfoil for the wing, we also decided to assign a penalty to NACA airfoils, considering that NACA airfoils generally have less than ideal performance at low Reynolds numbers, which is what our aircraft will be flying at. So after going through our down selection, we ended up deciding on the Selig 2091 airfoil, which is displayed here. We have a chord length of 11 inches, which corresponds to a thickness of 1.11 inches. Shown here is the 2D wind tunnel data for the Selig 2091. This is taken from the Selig report. You can see there's a CL max of approximately 1.3 and an alpha stall of 10 degrees in 2D. This was used as the basis for the conversion to 3D for the lift coefficient. After converting the data from the wind tunnel to 3D, we now have a CL max 3D of 1.45 and a stall angle of attack of 16 degrees. Moving on to CM alpha, which is displayed here, you can see that the values for CM alpha are all negative for this airfoil. Also shown on here is the maximum value for CM alpha, which is negative 0.0314 for alpha stall. Lastly, for the Selig 2091 airfoil, we have the drag coefficient presented as a function of angle of attack. This is the total drag coefficient for the wing, not just the parasitic drag coefficient, which is why it varies. And the drag coefficient is lowest at what will later be shown to be alpha cruise. Now we'll be moving on to performance predictions. Starting at the top, you can see our cruise velocity of 27 knots. This satisfies our range and endurance requirements. Our range requirement is 2 miles, which is obviously exceeded at 23.3 miles for our cruise range. We also have a cruise endurance of 46 minutes. This was determined by our maximum lift to drag ratio, or flag ratio. This is 12.11 at an angle of attack of 0 degrees, which corresponds to a lift coefficient of 0.433. You can also see the maximum range and maximum endurance. a maximum range of 24.5 miles, and a maximum endurance of 1 hour. That's primarily based on our battery, which will be discussed later. Here is the lift produced at Alpha Cruise. Shown here is our cruise velocity, which produces a lift force of 6.5 pounds, which is what we desire for SLEF at cruise. Shown here is the lift produced at Alpha Stall, where CL max occurs. We have a stall speed resulting from this of around 15 knots, and a lift produced at cruise speed at this angle of attack of 21.8 pounds. This will be used later in the structural analysis. Now Michael Blackwell is going to speak about drag estimation.
Looking at our drag polar graph and using a total skin friction drag of 0.00263, you can see in the red circle the parasite drag coefficient with a value of 0.026. And in the green circle, we can see our LORD max with a value of 12.11. Using a drag buildup method and an S-wet area of 26.2 feet squared, total aircraft drag was plotted versus velocity. In the plot, we can see our stall speed, which is 15 knots, represented by the yellow dot. The cruise speed is the purple dot, and the minimum total aircraft drag is a purple dot with a value of 1.08 pounds force. The equations for the drag buildup method can be seen in the appendix. And now Angel is going to talk about the aircraft structure.
For the structure section, we will be going over 2 wing load cases, 1 boom loading case, material selection, and component sizing. For the first load case for the wing, it is assumed that the wing acts as a cantilever beam with a distributed load placed on it from only the lift. The magnitude of this lift is 16.35 pounds, which is derived from the maximum lift of 21.8 and a factor of safety of 1.5. And since we will be looking over half the span for this cantilever beam, then you divide it by 2. This distribution is then calculated or approximated by strength approximation. All the other loads are assumed negligible. After we apply strength approximation to calculate our distribution, this is a result. It is an average of the elliptical and even distributions. From the lift distribution seen in the last slide, we get these shear and moment diagrams. From observation, we could tell that the magnitude of the max shear is 16 pounds and the maximum magnitude for the bending moment is 304 pounds and inches. For the second load case, the structure is analyzed using the skin panel method. This method assumes that there's lift, drag, pitch moment, and inertial weight loads applied to the structure. The lift has an elliptical distribution with a magnitude total of 16.35 pounds. The drag is assumed evenly distributed with a total of 1.1 pounds. The pitch moment is calculated with the lift distribution, therefore it's also have an elliptical distribution if pitch moment coefficient was used of negative 0.03. The weight was calculated using material and dimension approximations that gave us approximately 0.78 pounds for the skin only. This was then multiplied by an inertial load factor of 2.5 and 0.25 acting against lift and with drag. With these loads all accounted for, using the skin panel method, this is the lift distribution that we got. From the load case, seen in the previous slide, we get the shear moment diagrams, seen here. As you can tell, the maximum locations occur at the 0 axis, which is at the root of the wing. This gives us a maximum shear magnitude of 12.5 pounds and a maximum bending moment magnitude of 193 inches. For the boom, the structure is simplified into a cantilever beam with a moment arm of 36.25 inches, which is the distance between the aerodynamic center of the wing and the horizontal stabilizer, and a point load at 32.7 pounds, which is a lifting load of the wing. With the assumptions given in the previous slide, this gives us a maximum bending and shear to occur at the support. The maximum shear magnitude is 32.7 pounds, and the maximum bending moment magnitude is 1100 pounds per inch. For material selection of the spar and the boom, we picked the carbon fiber composite. This is because of its high strength and low density. Other considerations are balsa wood and aluminum, but their performance did not compare to that of the carbon fiber. For the skin, we opted for foam board, a commonly used in RC aircraft. This is laminated with heavy craft paper, and we are considering using plastic film to reinforce it, or even to use it as a sole skin. Further analysis will have to be made to make those decisions. For the wing ribs, we are approximating to use PLA or balsa, but at this point we have not made a decision. Further analysis and feasibility studies will be conducted. For sizing the spar and the boom, we first assumed a circular tube cross-section. Then we used a performance metric that looked over weight, stiffness, bending, and shear strength. The weight, stiffness, and bendings were weighed evenly at 30% each because of the importance of low weight, stiffness because we need to keep our aerodynamic shape, and our bending because that is our strongest force. Shear is not as great as bending and is not a big problem, therefore it is weighted only at 10%. If you'd like to see more information on the performance metric, you can see Appendix M and N. Using this performance metric, it's sized our spar to have an outer diameter of 0.5 inches and an inner diameter of 0.4 inches. This cross-section gave us a maximum bending stress of 4,200 psi and a maximum shear stress of approximately 450 psi. The boom cross-section is 0.75 for the outer diameter and 0.54 for the inner diameter, giving us a maximum bending stress of 3,900 psi and a max shear stress of 300 psi. The skin was sized assuming it was going to be load bearing and then bending only, but also taking into account the sourcing of the material. Therefore, we ended up opting for a 3/16 inch for thickness. This gave us a maximum bending stress of 615. As you can see from the previous slide, this 615 bending stress is greater than that can be taken by the skin material we selected. Therefore, stiffening the skin will need be required. In our initial assumption for the load-bearing skin, we did not take into account the bending load taken by the boom. Therefore, further analysis will have to be done to account how much the boom will account for the skin. This figure shows us our wing structure layout for half a wing. It shows us our approximate location of our ribs and our spars. This longest spar, which runs to the wingtip, is located at the quarter cord to resist the lift at the place where it is strongest. At the root of the wing, we see that we have 2 spars. This is to assist in resisting the location where most of the lift distribution is located at. This will help us out with our stiffness and to keep our wing aerodynamic shape. I will now pass it off to Andrea Dumitrescu, who will be talking about the weight and balance estimates of the aircraft.
For our weight and balance, we first took all of the hardware components that we knew we would be needing for the aircraft and determined their weight and added them up for a total of 3 pounds. Then we took the maximum takeoff weight of 6.5 pounds and subtracted that hardware component weight of 3 pounds to get an overall structure weight of 3.5 pounds. From this, using Roscom's historical weight fraction method, we determined the estimated weights of each structural component of the aircraft. In this picture, you can see the wireframe of DORA, and pictured on it are the estimated CG locations of each component, both structural and hardware. These were determined by taking the X distance measured from the tip of the nose of the fuselage and multiplying it by its respective weight, either estimated or taken from the internet. This helped in determining our overall XCG location of the aircraft. Here we have DORA's XCG location, which is estimated to be 17.1 inches from the tip of the nose, and we also have our X aerodynamic center location, which is estimated to be around 20.9 inches from the tip of the nose. In this section, I will be talking about the stability and control evaluation on DORA. Something that was changed since our last presentation was the internal layout within the fuselage, mainly shifting our batteries forward. This allowed for the XCG to also be shifted forward, which resolved our issue of a very, very small static margin, and now we are very stable with a static margin of 0.33. Static stability, we had both longitudinal stability and lateral stability requirements that needed to be met. For longitudinal stability, static margin needed to be greater than 0 and our CM alpha needed to be less than 0. Our CM alpha is our pitching moment coefficient. Both of these were satisfied. For lateral stability, we needed to have a CL beta of less than 0 and a CN beta greater than 0. Our CL beta is our rolling moment coefficient, where our CN beta is our yaw moment coefficient. Both of these were also satisfied. Because of the longitudinal and lateral stability requirements both being satisfied, DORA is predicted to meet all static stability requirements during flight. This graph outlines our pitching moment as a function of alpha, showing that if alpha increases, our pitching moment decreases. This is what we want in our aircraft, so this graph proves the merit of our stability derivatives. Similar to the previous slide, this graph shows our rolling moment as a function of side slip. It demonstrates that as our side slip increases, our rolling moment decreases, proving our merit of our static stability derivative calculation. This graph of yaw moment as a function of side slip shows that as our side slip angle increases, our yaw moment also increases. This proves that our static stability derivative that was calculated is accurate. Now I'm going to hand it off to Jacob Johnson, who will be illustrating how we did our control surface sizing for DORA.
Thank you, Andrea. So for our aileron sizing, we wanted to be able to make that banking turn of 55 degrees in a reasonable amount of time. Starting with trade studies, we looked at different chord ratios as well as span ratios. So starting with kind of a general drone UAV aircraft, we found a chord ratio of 0.2 and a span ratio of 0.1. And then these will be located at 30 inches from the mean center of the aircraft out to 38 inches, giving us a total area of 18.04 square feet. This configuration for aileron did give us a time to turn, or time to bank, of 0.33 seconds. For the elevator sizing, a similar process was went about. We looked at similar UAVs and drones to find a range of chord ratios as well as span ratios. And we went with 0.35 and 0.43 respectively. These are a little on the higher sides just because the horizontal tail is still kind of in the wake of the main wing and has some propeller wash to go through. So we just wanted to make sure we had enough surface area to be able to have the pitch that we're going to need. And each elevator had an area of 22.5 square feet, and there will be 2 of them located on either side of the horizontal tail. And finally, for our rudder sizing, the same process was followed. However, again, we did go with a much larger end of the ratios. 0.35 was pretty much on the very end of what we saw, and same with the 0.8 for span. This was because the main vertical stabilizer is right behind the main fuselage, having only a few inches above that where the horizontal tail is going to sit. So we went with a fairly large area for that of 18.04 square feet with a total height of 8 inches, and then this will sit just 1 inch above the bottom of the vertical stabilizer. And next I'll be handing it off to Chris Parker, who's going to be discussing our power.
Here is our propulsion requirements. This was all calculated using a mission analysis. The picture on the right depicts the mission that DORA will undergo. Point 1 is the takeoff and acceleration leg, which will require 3.6 pounds force of thrust. Point 2 is the climb leg, which will require 3.4 pounds force of thrust. Point 3 is the cruise leg, which will be in slough and will require 2.1 pounds force of thrust. And point 4 is our loiter leg, and that will require 3.8 pounds force of thrust. Next is the power consumption requirements. To do these calculations, we had to make some assumptions, including an installation loss of 20% and a propeller efficiency of 0.6. On the right-hand side, you'll see a table with the values of the power required for each portion of the mission leg. These requirements come from what the motor will have to perform to do the mission, including the largest value, which is the loiter leg of 587.1 watts. Here are our power requirements. Some of the parameters that the motor needs to meet is to have a weight of less than 0.35 pounds, meet the power consumptions as discussed before, have a factor of safety of 1.5, and an operational voltage of 11.8 to 14.8 volts. Here's the motor that we picked. It is an AS2820 long shaft made by T-Series. The reason that we picked this motor is because it has a nominal voltage rating of 11.1 to 14.2, which is within the tolerances that we wanted. It has a kV rating of 1050. Its maximum power output is 963 watts, which not only meets our factor of safety of 1.5, but also our power consumption requirements. And it has a weight of 0.32 pounds. Here's the propeller requirements. The propeller selected needs to meet the thrust requirements as stated before. It cannot exceed a diameter of 11.15 inches to make sure the tip does not strike the boom, and it needs to be a pusher propeller. Here is the propeller that we selected. It is an APC 11 by 5.5 MRP. The reason we selected this propeller is because it has a maximum thrust of 6.23 pounds force when paired with our motor, and meets both our safety factor requirement and our thrust requirement. It is lightweight with a weight of 0.8 ounces, has a diameter of 11 inches, which will ensure that it doesn't strike the boom, and it is a pusher propeller. Here are our battery requirements. The table shown has both our values and requirements for the battery. The top 3 are continuous nominal voltage, continuous current, and burst current, which are derived from the motor. The energy and weight requirements are from the range, and the flight time requirement is 46 minutes. Here's our battery selection. When looking at the requirements, we decided that it would be best to wire two batteries in parallel, so we chose the Turnigy 5.0. The reason that we picked this battery is because it met all our requirements, such as the burst current of 350 amps, energy of 3,700 watts, a weight of 2.4 pounds, and it gives us a flight time of 46 minutes. Andrea Gray will now be talking about the communications of DORA.
To begin my section, I would first like to go over the requirements for the autopilot and communication system. As you can see in this slide, I have established 5 requirements, which are: correctly gather all sensor data from the onboard and peripheral software, ensuring that there are no data overflows in the processor and that all data retrieved is accurate. Ensure the correct sensor data is input within the code for each scanning iteration. This may be handled by a software interrupt or a loop that gathers data from each sensor at a constant interval without skipping over any sensor or data manipulation errors. Calculate autopilot commands based on the sensor's data with the equations necessary to turn raw hardware readings into the necessary components that will then be used to determine if DORA is functioning and reacting correctly, such as pitch and angle of attack. Identify and mitigate all hard real-time and soft real-time code faults and bugs. Hard real-time errors are bugs that will cause mission failure, and soft real-time errors are those that will delay the system, but not cause a total mission failure. Code in multiple fail-safes to ensure the safety of DORA. These fail-safes will be triggered if there is a software error, firmware error, or hardware error, and will take over the drone's maneuvers to abandon its mission and land safely so that the risk of damage or loss is reduced. This slide shows the 3 main flight controllers that were studied before determining the controller that would be used for DORA. There were 5 main elements that we studied for each controller: cost, weight, dimensions, data processing speed, and required input voltage. The best option would be that which has a relatively low cost, weight, dimensions, and required voltage input, while having a high processing speed for the real-time calculations needed. From the data in the flight controller specifications table, each of the 3 controllers were then put into a decision matrix to weigh each of their 5 elements and determine which option to use for DORA. As you can see from the decision matrix, the PixHawk 4 was determined the best option out of the 3 for all 5 requirements shown. The PixHawk 4 has an autopilot system that can be altered for the user's required application. The autopilot uses 2 compatible integrated development environments, or IDEs, to edit and compile the software and firmware before flight, and to upload and monitor the elements within flight. The autopilot software will use the onboard and peripheral sensors to gather real-time data about the flight and then react and correct any data that may be detrimental to the mission, such as an adverse angle of attack due to a wind gust, as an example. The autopilot will correct multiple elements, such as DORA's attitude, altitude, and heading, by reading the sensor's data and manipulating the commands sent to DORA to maintain a flight within safe boundaries. The system will be coded in the C programming language, since this is the language used by the PixHawk's autopilot. The system will also use the hardware data within the software calculations for the flight control. This slide shows the hardware connections for the peripheral sensors that will be required for use by the PixHawk. These components were chosen by recommendation for fixed-wing aircraft of DORA's size by the PixHawk's use guide for best performance, durability, and compatibility. This slide subsequently shows the data for each of the peripherals that will be used. This information is included for the viewer's further understanding of each component. However, none of this information will be necessary for the software's development. To focus more on the software development of the project, I have included a flowchart that represents the flight stack for the Pixhawk 4's autopilot system. This flowchart shows a high-level view of the components of the system and how the data flows between them. For further information on high-level diagrams, please refer to Appendix O at the end of this presentation for the system's block diagram. This diagram, unlike the high-level diagrams before, shows how the mathematics of maintaining flight are used by the system for flight control. This specific diagram shows how the sensor's data, once read and input into the software, is transformed into a single data element input into the servo motor to control the attitude of DORA. The arrows show the flow of data as before. DORA will have 4 servo motors on board to control the aircraft. The initial choice for the servo motor is the Sunfounder Metal Gear Digital RC servo. This motor has not been evaluated against other motors in a decision matrix yet, but I plan to complete the selection for the gathering of materials by next semester. The torque of this motor is determined on the input voltage, which can be either 4.8 or 6 volts. The torque is based off the requirement to move the control servo with the max load at max deflection, keeping the speed of reaction in mind as well. For the projectile, the Petra team has recently decided not to include a signal beacon for retrieval. Therefore, DORA will include a camera to determine the location of Petra instead. The camera hardware has not been determined yet due to the recent change, but it will require a wide range angle for a large field of vision, and it will be mounted at a slightly forward-facing angle. The camera will be mounted on the front underside of DORA as seen in the graphic. Furthermore, it is of note that the camera, similar to the other peripherals, is easily integrated into the Pixhawk system and is well documented by the Pixhawk development and use guides. For the subsequent semester, I hope to acquire the Pixhawk flight controller immediately at the start of this semester, or earlier if possible, to review the system and the code that comes with the flight controller and begin editing the code for DORA's application. With the editing, I will also be testing the code often with the test data to see and understand how the controller responds exactly to ensure a safe mission for DORA. Along with the testing, there will be multiple fail-safes that I will implement and test as well, so that when the controller can be integrated into DORA, there will already be a backup system ready in case of failure. Once I understand the Pixhawk code and IDEs well enough, and before the integration with DORA, I will then begin the second round of testing and debugging for each peripheral required. This can be seen by the spiral model on the slide, with the yellow being the portion already completed this semester. The inner loop after the completed portion depicts the testing and development with the Pixhawk flight controller, and the outer loop being the final testing and development with the flight controller and peripherals, followed by any post-release debugging needed after the actual flight testing when DORA begins. I will now hand it over to Andrea to discuss cost.
Outlined here, we have all of the products that we will be ordering in order to successfully build DORA, along with their quantities and their respective costs. For a lot of these products, we're ordering more than what is needed. For example, we're ordering 10 propellers and 3 batteries instead of 2. We are doing this with the purpose of making sure that if something breaks or if something's defective or if we cut some kind of material too short than what is needed, we have enough backup products to make sure that the program plan doesn't fall behind. Now I will be talking about our risk assessment. For DORA's program plan, a total of 8 risks were identified and evaluated and rated on their severity of occurrence versus their probability of occurrence, and seeing how they would impact the program plan. Listed here are the top 3 risks that posed a threat to DORA's program plan. The 8 that were evaluated, as well as the graph that was used to determine the risk level, can be found in the appendix. For the first risk, we had that if wind tunnel test data finds drag is higher than predicted, then DORA will not meet performance requirements. This would cause DORA's program plan to slip. In addition to risk 1, risk 2, which is if the boom fails structural testing for tail loading, then the program plan will fall behind. For risk 3, if our purchased commercial off-the-shelf parts are defective, including the backup ones, the program plan will be delayed. Here we have a table outlining the 3 risks that were mentioned in the previous slide, and their severity of occurrence ratings, their probability of occurrence ratings, as well as their impact to the program, which is the product of both the severity of occurrence and probability of occurrence ratings. And the level column in the farmost right is moderate for all 3 because in the graph that can be seen in the appendix, they were the only 3 that fell into that yellow zone. Oliver Davis will now be talking about the labor hours worked over the duration of this semester.
Thank you, Andrea. This slide shows a graph which shows the semester split up into weeks and the amount of hours that have been worked over the course of the semester in blue. The red line shows the predicted number of hours that were originally estimated to be worked over the course of the semester. As you can see, the number of actual hours worked consistently stayed below that of the predicted hours to be worked. This is likely because of the smaller size of our team compared to a normal size team of about 10 or so, and also the wider scope of our project, which had some team members working on other aspects of the project which were not DORA. So those hours were not included in these estimates. The predicted labor cost of our project is shown here. The total cost of labor hours that were worked this semester was just under $166,000. This number was generated by taking the total number of hours worked by person in 5 different categories. Those were manufacturing, engineering management, engineering technical, administrative, and professional development, each with different hourly rates associated to them. So that is how that number was generated. A predicted future cost for next semester is just under $226,000. This number was estimated by information from previous teams in their detail semester and using that to estimate the total number of hours that a team of our size would work. And this leads us to a total estimated cost of near $400,000 in terms of labor. I will now be going over certain aspects to conclude this preliminary design review. Below is a table showing our requirements evaluation and just showing which technical aspects of our aircraft satisfy certain requirements as stated at the beginning of our presentation. Our first requirement, which is our 45-minute flight time requirement, DOR-01, is satisfied by our calculated maximum endurance of 1 hour. Our 2-mile range requirement, DOR-02, is satisfied by our max range being predicted at 24.5 miles, which more than satisfies this requirement. DOR-03, which is our wind speed requirement, is shown to be satisfied by multiple parameters, as is DOR-04, which is our temperature performance requirement. DOR-05 and DOR-06 relate to our cruising altitude and the ceiling of the aircraft. These are both shown to be met by our air density parameter, which shows the density of air that our aircraft will be able to perform in. This is a lesser density than the altitude we will be flying at, meaning we are able to successfully fly at the altitudes that we need to. DOR-07 is our turn radius requirement, and this is shown to be satisfied with our cruise velocity and L over D parameters, which correlate to a bank angle and turning radius of less than 40 feet, which is our requirement. And DOR-08 is shown to be met by our planform area of 6 feet. This allows us to carry loads that are equivalent to or less than the excess lift that can be produced by the planform area of our wing, which in this case is 6 square feet. Our design today is shown here on the right of the screen. Some of the main parameters of our aircraft are the weight of 6.5 pounds, our wingspan and lengths of 82 and 56 inches respectively. The airfoil of the wing is a Selig 2091. This was covered in our aerodynamics section. Our motor is the AS 2820. This, along with the propeller, will create enough thrust for us to have successful flight in all conditions, that being in the hand launch, the climb, the acceleration, the cruising, and the loitering legs of our flight. And then we also have a battery selection that will allow us to meet all the requirements as stated on the slide before. And this will allow us to fly for over 45 minutes to complete our mission successfully and have a safe landing of DORA back at the launch point. Some future tasks are shown here in our program plan. The future tasks are shown in green. That is the design verification and the manufacturing stages of our project. The design verification will consist of wind tunnel testing and structural testing. And then in the manufacturing phase of the project, that consists of us purchasing commercial off-the-shelf parts and then printing some of our CAD parts, and this will lead to some structural testing. And then hopefully at the end of our project, we will be able to do a flight test. Our team would like to acknowledge the help of the professors listed below for just the time and knowledge that they have given to us over the course of this semester to help us complete this project to the best of our abilities. So we greatly appreciate the help of them. If you have any questions regarding the information presented in this PowerPoint, please refer to the appendices in the following slides or reach out to any of the team members who presented this presentation. I would once again like to thank you for your time, and we hope to hear some feedback from you soon.